All right, recording is rolling. Welcome to Wednesday, September 27th. We're going to just chug through a bunch of textbook puzzles today. I signed all these to you guys, except for number 41 crate, although one of your take-home quiz questions looks a lot like this one. Right, so yeah, we're going to keep a pretty good pace today. I'm going to go a little bit faster than I normally do, right? But it's like the same type principles you guys have seen over the last like 2.5 weeks. I do have a number key printed that I'm gonna give you guys tomorrow. So you guys see an AP version of some stuff you guys been doing. What are you guys gonna bring on Friday? Laptop for this this Tesla open bin. All right, go through that. All right, and what's due on Monday? Your take-home quiz. Take-home quiz. All right, so let's check through these puzzles. All right, number 19, bird feeder. Actually, I think if I remember, I think we started on this bird feeder question yesterday. Got about halfway through it. I'm gonna go ahead and start that one from scratch. So if you're good with what we've done so far, then you get a quick review. And if what we did yesterday was kind of confusing, you're like, wait, what? What's going on? Then well, get some good review too. Right, so it's first thing again. Okay, so I'm gonna introduce a Cartesian system. There's something about like a bird feeder hanging in equilibrium. There's a couple of cables pulling at different angles, right? And the question is, what's the tension in each cable? So the principle that we're going to use to solve this is the sum of the forces goes to 0 newtons, right? And that's true along each axis. So we've got this Cartesian system, which right, I'm just right, so x direction, y direction. So in the x direction, and whoops, the sum of the forces in the y direction. It's supposed to be a sigma right there. Right. The sum of forces, you can also call that the net force in the x direction, the net force in the y direction. Right, so here's the node where all three cables come together. Okay. This bird feeder is hanging straight down. It's pulling straight down with the weight. They told you the weight of the bird feeder. I'm just going to go ahead and use their weight, 150 newtons. Right. So it's a 15 kilogram mass. It weighs 150 newtons. Right. Then there's this tension A pulling up and to the left. Or wait, what did they label that? I'm thinking of something a little different. Here, let's just call it tension left. Tension left, right? And then there's another cable pulling kind of this direction, sort of, right? I'll call it tension on the right. Tension on the right. Okay, is that? Okay. So you go. There's your free body diagram, FBD, for that bird feeder. It's got a weight and a couple of cables this way. Right? Now the tension in the bottom cable is the weight of the bird feeder, which is 150 newtons. Okay, so we got that one. Okay. What about these other cables, the left tension and the right tension? Okay. So the principle that you're using to solve these is this right here. Right. So you've got something crazy going on, three different forces. Right. Imagine like a truss bridge. If you're an engineer one day to like, design structures, you're gonna use this like over and over, like every day of your life. You're gonna use this, right? So horizontally, everything cancels out. Like these components is horizontal. This one pulls right as much as this one pulls left. That's that condition. Right? Here's what it looks like spelled out, like as an equation. Right? See, something to do with like sine or cosine of these angles, alpha, beta going on. Right? Actually, cosine of those angles, right? And then each of these is pulling up some, strictly up, has to balance with this weight pulling down. That would satisfy this condition here. Right? So here's up, and then down. Right? It's playing off the sine of alpha and sine of beta for those. Right? So we're going to do exactly that. We're going to do exactly that. Okay. We're going to do. So I need to break these forces into components. Now I was trying to draw this approximately to scale, which means that, ooh, why did I make this right tension really short? So what I'm claiming by drawing it really short, what I'm claiming is that it's going to be a relatively small tension, right? See, like on the picture, you just see like some cables going. Oh, I forgot to label the angles. I'm going to label this angle 60 degrees. I'm going to label this angle 30 degrees. How about that? Now, how would I know that? Well, I actually know that this is going to be a relatively small tension because of this top condition, some of the force exposed here. Let me show you guys. When I break this into components, if you don't see it right now, then you're about to see it. It's about to pop out of the page. Why did I make the right tension really short compared to the left tension? Okay? Why do I think the left tension is going to be relatively big and the right tension relatively small? Left tension is, well, this much left and this much up. Right tension, this much right and this much up. Ah, do you guys see now? If you didn't see it before, I bet you see it now. This one pulls right as much as this one pulls left. Okay, that's how I know something about the relative magnitudes of those things, right? Reset. And start labeling this. Let's call this tension left. We don't know what that is yet, but whatever it is, times cosine of 60 degrees would give us that. And tension right times cosine of 30 degrees gives us that component, right? And this better be balancing out. That's going to be one of our equations. Right? Then here, while I'm getting components, let's go tension left times sine of 60 degrees is this one, and tension right times sine of 30 degrees is that one right there. Wouldn't that be true? Just like that? Okay. And then set up some equations here. All right. So we start with this top expression. The sum of the forces in the x goes to 0. So this minus this has to go to 0. So tension right times cosine 30 degrees minus tension left goes opposite direction. So there's subtracting from each other. Cosine of 60 degrees has to go to 0 newtons. Right? And then this other condition is in the vertical direction, in the y direction. So these two components conspiring up have to exactly balance with this weight pulling down. So I get the equation for that. So tension left times sine of 60 degrees plus tension right times sine of 30 degrees, right, minus this weight, which, well, we know it's 150 newtons, so I'll just call it 150 newtons, right, is equal to 0 newtons. Like that, right? This right here, that is your system of equations. You guys see two independent equations with two unknown values. We don't yet know what is tension right and tension left, but two equations, two unknowns, that means we can solve it. Okay? Now, different methods you can use to solve it. You can use substitution, you can use elimination. If you're good at matrices, you can even use that. I'm just going to pick a method and go with it. I'll use substitution. So I can clean this up a little bit. Let me rewrite this system cleaned up a little bit. Because cosine 30 degrees, is that like root 3 over 2? Cosine is 60 degrees. Is that like 1/2? And so on. That's it. So root 3 over 2 tension right minus 1/2 tension left. So as fractions. So right, looks a little cleaner. Goes to 0. Right. And then the second expression, sine 60 degrees is also root 3 over 2. Root 3 over 2 tension left plus, okay, sine 30 degrees is half, so 1/2 tension right. Right. I'll go ahead and take this 150 newtons and just slide it over. Say this is equal to 150 newtons. It's also newtons, right? Something like that. Okay. So this is the same system. It just looks a little cleaner, right? Like that. Okay. All right. Oh, here's what I do is take this top expression. Let's say I solve for one of these, either TR or TL, and then substitute it into the other one. How about TL I'm going to solve for? How about that? I'll solve for TL first. And so if I do that, that's going to look like, say I can multiply both sides by 2, add that over, and here, well, 1/2 TL would be root 3 over 2 TR. Right. Therefore, TL, the left tension, is equal to the square root of 3 times the right tension. Okay, so great. I'm gonna kind of dash outline that. That's a really critical step that we've hit. Right. See, I still don't know what the left and right tensions are, but I know proportional to each other what they are. Right. Square root of 3, is that like 1.73 something? Right. Okay. So one, right, if you know one, you can figure out the other. Right. We're gonna take that and expression and substitute it right up into TL. Right. So now let's take this second equation and come down and write that. Okay. So I got root 3 over 2 times TL, but I'm not going to write TL because I know TL is equivalent to root 3 times TR. So I'll put that right here, root 3 times TR. Right. Plus this 1/2 TR is 150 newtons. Right. Good so far? Okay. Oh. Ooh. Okay. It can multiply everything by 2. Do you guys see I have 3 terms? Boink, boink, boink. 3 terms. Can I multiply everything by 2? Is that okay? Okay. Guys, what is root 3 times root 3? 3. So 3 times the right tension plus another right tension equals 300 newtons, because I multiplied everything by 2 to get rid of those fractions, right? You guys see 4 times the right tension is right there, right? 4 times the right tension. Right, so 4 times the right tension is 300 newtons. Okay, so we're about to get the right tension, because all you have to do is take this 300 newtons and divide by 4. Is that 150, 75, I think, 75 newtons, right? 75 newtons. Right, I'm going to finish that over here. So tension on the right side, therefore, would be 75 newtons. Okay, that's one of the cable tensions right there, right? Here, that just continues from this process here. Okay. Right, so a pretty good thing to do is when you get an answer, right, look big picture, then be back to this free body diagram to say, does that look kind of reasonable? In fact, how I drew these free body diagram vectors, I tried to draw them to scale. I think I did a pretty good job. Okay? Does that look approximately half of that? Because that's what I'm claiming right here. Because 75 newtons, that is half of 150 newtons, doesn't it? Ooh, does that look about half of that? It sure does. Okay, so yeah, I'm pretty happy with that. Right. Now let's get tension left. Remember this part that I dash outlined right here? That's the relationship between the left tension and the right tension that we used as a substitution. I can just bring that on down right here. Tension left, I remember from before, was √3 times the right tension. Right? I can now substitute 75 newtons right in there. Okay. So what is 75 newtons times the √3? Because that's what we're looking for. Is the √3 times 75 newtons. That's like tension left is 129.9 newtons. There you go. Okay, you guys got that? Okay, so a lot of algebra, but remember the physics principle really comes back to the system of equations here. The forces have to sum to 0 in each direction. Oh, yeah.
Isn't square root really about is square root? That's really about like 0.57.
√3, 1.73. There you go. Okay. There you go. All right. All right. Next one, number 28. Ooh, one of your take-home quiz questions looks a lot like this. Actually, the take-home quiz question is a little more complicated than this because this one here says a frictionless surface, and you guys gave some friction. So I'll solve this, and as they go along, though, I'll point out the difference. Like I can amend that a little bit to solve it with your take-home quiz. Okay. We've got this like this inclined at-width. Okay, so this is like a combination of a lot of things in the last couple of weeks. Right? Got incline was a concept, at-width was a concept, and now we're combining those two. Your take-home quiz even has friction on top of that, so that's like another concept. Right? They're putting a 10 kilogram mass hanging over here. Okay? So I bet that's going to weigh about 100 newtons. Okay? They got this 5 kilogram mass over here, 5 kg. Right? What was this angle right here? It was 40 degrees. They're calling it 40 degrees. Okay. So there you go. There's our setup. Okay. Now this is definitely going to accelerate counterclockwise. You guys see that? Okay. Sometimes it's a little ambiguous. Like, what if I put like 11 kilograms over here? I said, well, then it probably depend on what this angle was. Probably still accelerate that way at 40 degrees, but okay. Sometimes you have to make a guess, right? And that guess would be particularly important if there was friction, because depending on which way it's moving, the friction force is going to oppose that. So like on your take-home quiz, you might have to make an educated guess on which way it's going to accelerate. Actually, here, I'll just, like, I think I had it that way. Right? It's the hanging one, I went ahead and just like accelerate downward, right? But I think you can figure that out on your quiz anyway. Now let's do a free body diagram for each one of these masses and then start to make sense of this. There are two questions in the book. One is, what is the downward acceleration of the large mass? So basically, how much is it accelerating? And the follow-up question is, what is the tension in the connecting string? So I'm thinking, how many newtons of force is that right there? Mg equals, you guys think 100 newtons? 100 newtons, right? 10 times 10, 100 newtons, right? And this block over here, well, it'd be half as much. Ooh, I should have made this a little longer. Here, let me make this longer just so I can try to keep everything to scale and hold it, right? 100 newtons. It's like half of that be about, still not, okay, maybe kind of close, right? You guys think that's about 50 newtons right there? 50, right? Right, mg equals, right? Yeah, oh yeah, true, 49 more precisely, right? Okay. Right. I'm gonna split that into components. So, you guys remember if I had this rotated Cartesian system to align with the surface I've been telling you guys to do? Okay. So that means part of those 50 newtons is pushing the block into the incline. And part of those 50 newtons is trying to drag the block along the incline. I just dashed those components. You see how I dashed them? Okay. Ooh, what's this angle right here? 40 degrees. There you go. Okay. So this must be 50 newtons times sine of 40 degrees. And then here's your 50 newtons times cosine of 40 degrees. Okay. Oh, there's also a normal force on this block. And draw that. Normal force, which you guys know is whatever this is, comes out to be. Let me get some values here. All right, what is 50 newtons times sine of 40 degrees comes out to 32.1 newtons. Okay. And then if I flip in a cosine, that ends up being 38.3 newtons. Right? And you know, this right here would also have to be equal to, there you go, 38.3 newtons, right? So that it balances this one out, right? Now, as long as this string is pulling parallel to the surface, if it's pulling at some weird angle, then things get a little wackier, but all right, you guys imagine that, right? Okay, right. Now there's also an internal tension force. There's a tension pulling this block back this way and this block like this way, right? I'm gonna ignore that for now, but I'll come back to it later, right? Because one of the questions is, what is the tension, right? Now, there's a couple of ways you can solve for the acceleration. You can do a micro approach and set up system equations, free body diagram of each one, right? But I'm going to do the systems approach that I normally do with you guys. So the acceleration, like system as a whole, because they're both the same magnitude acceleration. Oh yeah, go ahead.
Are you able to find the acceleration with Newton's second law?
Exactly. That's what we're going to do. Yeah, second law. So we're looking for net force on total mass, right? And here, the net force, what's the net force? Well, I'm looking at two forces that are competing to drive the system. Two forces that I care about, right? I care about this hanging weight right here that's saying, let's go counterclockwise. And what's resisting that is this component of this weight over here, this 32 newton saying, no, let's go back clockwise. Is it right? The normal force and the cosine component of the weight cancel out, so I don't worry about those. It's not accelerating that way anyway, right? So these two are competing, right? Now here's where I want to pause, because your guys' take-home quiz has one more complication, which is friction. Now, suppose you have it going counterclockwise in this case. So you say, okay, well, the hanging weight's going to fall. Right? If that's true, then which way does friction point on this block? Down to the right, right? Which would be in conjunction with this 32 newtons, right? So here I'm about to do the acceleration of the system. Well, the net force would be 100 newtons minus 32 newtons, right? But you guys would also have to furthermore subtract the friction force, right? You say also minus the friction force, right? Pause there. How would you get friction force? Friction force is equal to what? What coefficient of friction times the normal force, right? So that's actually why I calculated the normal force here, even though we don't actually need it for your textbook problem. You guys do need it for take-home quiz, because you need to find that, so you can pop it in there, then take whatever coefficient of friction I gave you. Right? You can find the magnitude of that friction force that is conspiring with the 32 newtons to resist the 100 newtons. Okay? Right. So here we go. There's your net force. What's the total mass?
10 plus 5?
10 plus 5, yeah. 10 kilograms plus 5 kilograms. Yeah, that's all being moved. Right. So put it all together here. We got 100 minus 32.1, all acting on 50 kilograms. Okay. I'm looking at like 4.53 about meters per second squared. I think in the solutions I wrote a few years back, I used like 9.8 meters per second squared for gravity. Here I'm using 10, so slightly different numbers, but should be about that, right? One other detail on this is actually a magnitude of acceleration. So if you put it on a direction, that's downward for the hanging block, and that's kind of up and left for the sliding block, okay? Right. Now the other question is, what is the tension in the string? So I'm gonna go back and amend this free body diagram, because I have the external force strong, right? But now what about this internal force? Do you guys think that tension is, here, I'll go to F sub T, is the same for both blocks? So draw out the same magnitude for both blocks, because there's only one tension in that string, right? And it better be larger than those 32 newtons, but less than this 100 newtons, right? So it's like a Goldilocks force, right? Okay, so that there's a net force this way in this block and a net force this way in this block, okay? So here's where I'm going to pick one of these blocks and set Newton's second law of motion as it applies to that block. And remember, I know what the acceleration is, right? Which one do you think is the easier one to analyze? The one with all the crazy forces on it, or the one that's just strictly up and down with two forces? Yeah, probably that's the easier one. You could do either one. You'll get the same answer. But I'm going to pick the one that's just hanging, because it'll save us a hot minute here. Okay? So we've got some here's what we got. Forces. I got mg is 100 newtons down. I got some mystery tension acting up. Here, I'll do F net equals mass times acceleration just for that hanging block. Okay. Now the net force is 100 newtons down minus mystery tension up. That's going to result in, that block was 10 kilograms, okay, being accelerated at how much? 4.53 meters per second squared. 4.53 meters per second squared. Okay. I'm defining down as the positive direction. That's why I'm doing like the down minus up. Right? It's also accelerating that direction. So that's why I'm calling it a positive value for acceleration. Be careful with your signs. Earlier in my first period class, I accidentally swapped directions and got something totally wrong. But okay. So solve this here. This would be 100 newtons minus the tension force, therefore equals what, 45.3 newtons. Okay, add that over, subtract that over. Tension force is 100 newtons minus 45 newtons. All right, that's like 54.7. There we go. Right, so it's the tension in the string. Tension in the string right there. Okay. Okay. Okay, we're good there. Okay. And so pretty similar. It's just same stuff we've been doing the last couple of weeks, but it's just combination now, right? A little bit more complex. You guys seeing plenty of inclines, you guys seeing plenty of outwards, and we're just putting it all together. Yeah. Oh, what's that? This one? This one? Okay, hang on.
So when you have a tension force, you just attack the tension force following the attack.
Yeah. So okay. So if there was friction, okay, then what I would do, I'm gonna go back a few steps. Right. It was this part where we're calculating acceleration. I did this again from a systems point of view. I'm looking at like as a whole. Right. Okay. So here what I have without friction is I have two forces in competition. I have this guy saying let's go counterclockwise versus this guy, this little component saying let's go back clockwise. So subtracting there. Right. Yeah. If there was friction, then first you'd have to figure out which way this is moving. Right. So let's say you say, oh, it's probably going to be moving this way. Right. Therefore, friction is actually pointed that way. Right. Okay. You get the magnitude of the friction force by doing this. You'd have to know coefficient friction, multiply it by this normal force, and then you have magnitude. Suppose it's like 20 newtons, for example. So we go 20 newtons. Right. Then 20 newtons is acting in the same direction as the 32 newtons. It's both trying to slow it down. So I do 100 minus 32 minus 20. Okay, and then divide by the total mass and give you the acceleration. Okay. All right, okay. All right. Next one. All right. Next couple of questions are a couple of outwoods. One's like a modified type. AP calls this a modified outwood, right? And then we have the classic double elevator outwood. What's the acceleration? What's the tension? Right? And then there's also but we'll get that far. And then there's also another follow-up question. So again, trying to keep kind of a fast clip right here. They have this guy M1 as, see, 5 kilograms. Start over. I'll give myself some room in there. Perfect. This guy is 5 kg. Hang it over the edge. And this guy is 10 kilograms. So 10 kg. Right, something like that. Okay. They said 0 friction, so frictionless surface right here, right? Which is the same setup that you guys had for when you guys did it, right? Because you guys had a Hot Wheels car underneath here to make it basically frictionless, right? Okay. So here's how this plays out. That's how it's going to play out, right? Just ignore this friction bit right here, because if there's no friction, right? You guys remember the second box was like the answer to your lab, right? What's the acceleration? Right? So there's a bunch of forces going on, but the weight of the hanging one is the only external force that really matters that's driving the system. Okay? So the block up here does have a weight, but that's balanced out by the normal force. Those two cancel out. That's not actually driving the motion. Okay? The mass of this block matters. If it's more massive, it's going to slow down the system, but only because of its inertia, not because of its weight. Right? There's a tension force, but that's just internal to the system. Right? Now, if you analyze each block individually, then maybe you could set up a system of equations that the tension matters. Right? But from the system's point of view, like as a whole, right, this weight is driving the whole system. Right? Okay, so we're saying 0 friction, 0 friction. So let's do that. So I've got a down force right here of 100 newtons, right? And that is the external force that matters, right? So these two cancel, mg with normal force. There's some kind of internal tension that we'll figure that out later. Okay. I bet it's the same tension force for both though, whatever it is. Okay. So from a systems point of view, we've got net force on mass total. Okay. And that's 100 newtons. 100 newtons is driving the whole system. Remember, everything else like cancels out or is internal. There's no friction. Okay. That's moving, what, 10 kg plus 5 kg? Wouldn't that be true? Just like that? Let's see, what is that? What is 100 newtons moving 15 kilograms? That's like 6.67 meters per second squared. Okay. Okay. That's the downward acceleration of the hang one. That's also the sideways acceleration of the top block. Right. Follow-up question: what's the tension? So we could analyze either block. Eeny, meeny, miny, mo. Well, let's say I pick this top block here. Right. Top block. So I'll do F net for the top block equals the mass of the top block times the acceleration. Okay. We know acceleration. Pop that in there. Here's the mass of the top block, 5 kilograms, right there. 5 kilograms, 6.67 meters per second squared. Right? That's going to give us the tension in the string that's causing this guy to accelerate that much. Right? That's 5 times 6.67. Looks like 33.3 newtons force. That look right? Like that? Okay. Well, let me check my answer. Right, so I just got that this tension is 33 newtons. Does that mean this tension is also 33 newtons? Let's figure out what's the net force there. What's 100 minus 33 newtons? Right, it's like 66 newtons, 67 newtons. Right? If I have 67 newtons acting on 10 kilograms, this block should be accelerating down at 6.67 meters. Ah, look at that. It is. Right, so I just confirmed my answer. Went back and checked it for the other block. Right, it checks out. Okay. Okay. So there we go. Acceleration, tension. The next question is your classic double elevator. It's number 38 thing. What numbers do they use here? We got 3 kilograms versus 5 kilograms. So now we're back to this, right? We've done a number of these the last few weeks, right? 3 versus 5 kilograms. So 5 kg right there. 3 kg right there. Right, just like that. Right. Now there are 2 external forces that are competing. Here's your 50 Newton weight. Here's a 30 Newton weight, right? So this weight, I guess those are different masses, different weights. Okay. Right. Later on, we'll care about this tension that's like this Goldilocks force. It's the same for both. It's larger than the small weight. It's smaller than the large weight. So they can each be accelerated in a different direction, of course. Okay. Okay. But we're not going to worry about that quite yet because I'm going to solve this from a systems point of view. I'm doing this right here. Okay. So we've got one weight saying let's go clockwise, the other counterclockwise. Right? Those are subtracting from each other. Okay? And that net force is driving collectively both masses. And so here's the answer to recent lab. Okay. So the acceleration from a systems point of view has to be 50 newtons weight minus 30 newtons weight acting on 5 plus 3 kilograms. Okay, so that's a 20 Newton net force acting on 8 kilograms. That's 2.5 meters per second squared is the acceleration. Okay. So if this was an AP question, it'd probably be specified like that's the downward acceleration of the large mass, or that's the upward acceleration of the small mass. Accelerating opposite direction. Okay. Okay, let's figure out the tension. Tension, I'm going to focus on either one or the other block. So how about this 3 kilogram guy? There. Okay. So let's do F net on the 3 kilogram guy is equal to the mass of the 3 kilogram guy times the acceleration of the 3 kilogram guy. Okay. Now the net force is, well, you got the tension up that we're solving for minus the weight down, which is 30 newtons. Right? So that difference in forces is equal to, of course, 3 kilograms times 2.5 meters per second squared, because it goes right there. Right? Because we found that. Right? That looks like 7.5 newtons right there. Add over 30. Is that tension force? It's like 37.5 newtons, you guys think? Right? let's see, would that make sense from the other block? Oh yeah, look at that. 37 newtons is less than 50 newtons, which allows the other one to accelerate down. Okay, so that checks out too. Okay. Now, okay, you guys good so far? Okay. This is all like review type stuff, right? You guys have seen plenty of these so far. Right. There was a third question. They flip over back to kinematic motion. Question C, because there's question A and question B. Question C is, how far does this whole thing move in the first second? The first second, 1 second of falling. If you want to know how far and how much time, and you have acceleration, starts from rest, does that sound like a job for the first kinematic expression? Right? Here's the college version of that. X equals 1/2 AT squared. Right? X is 1/2 AT squared. Right? Starting from rest, you can use that. Notice I didn't say GT squared because it's not full free fall. Right? So let's go 1/2. We got 2.5 meters per second squared. They said for 1 second. So I'm squaring 1 second. Okay, 1 squared, so 1. Here, mental math. Is that like 1.25 meters? Right? You can call that 125 centimeters if you like. Okay, so just like a really long string, it would move that far in the first second. There you go. Okay. Yeah, pretty good review type questions going on there. Right. All right, hockey puck, number 46, hockey puck. Okay. Hockey puck. 36. So we got a long stretch of ice. This puck right here. Right. And we're going to strike that puck to give it an initial velocity to the right. Right. And then we're going to let it slide. It's going to slide. It's going to come to a stop. Right. They did not give you any numbers on this one. They said there's okay, we call this V naught, initial velocity. They said there's some coefficient of kinetic friction, UK, between the puck and the ice. I guess the puck probably has some mass M. And we want to figure out, let's see, what's the acceleration of the puck? Now, acceleration in this case would mean like what rate is it slowing down, right? And furthermore, what distance does it go? Like what total distance d does it travel to a stop? Okay, right, so first part is going to be here, let's do a free body diagram. I bet this puck has a weight mg. I bet it has a normal force that's exactly balancing out that weight. So in the back of my mind, I'm thinking, that's equivalent to mg because flat surface, nothing crazy going on. Right? That's satisfied by this condition. Some of the forces in the y direction goes to 0 newtons because it's not accelerating up or down for sure. Right? Slow down horizontally, but not vertically. Right? And should I draw a friction force counteracting the motion? Right? F sub FR, right, like that. Right. Let's do a little proof right here. Right, now this should be something that you should be able to figure out from scratch. I'll do it right in front of you guys right here. Newton's second law of motion. Net force equals mass times acceleration, or A equals F over M. You do it that way. Okay. Guys, what force is the net force on that puck? Friction, because the normal force and the weight balance out vertically. There's one horizontal force, that's what's slowing it down. So this is the friction force. Right, mass times acceleration for the puck. We're trying to figure out what's the acceleration. Okay. Oh, guys, what's friction force equivalent to? Is that coefficient of friction times the normal force? Oh, and what's the normal force equivalent to? The weight, right? Because of this condition here. Right? So I can substitute right there and say UK times mg is ma, right? At this point, what cancels out? The mass of the puck. Right. So here's the rate that it can slow down. The rate the puck can slow down is the coefficient of friction between the puck and the ice times the gravity field of the planet. Okay? Now that is actually already on a poster in this room. That's bam. That's that right there. Car breaks to a stop. Just replace the car with a hockey puck. It's the exact same thing. Look at that. Same thing. Same outcome. Okay. You guys remember, really classic physics question. It's always asked. If you guys go to college, this is gonna be a question that comes up. Okay. What happens if you like triple the mass of the car? So you like load it with a bunch of groceries and maybe some lead weights for fun. Okay? And then same tire, same road, same initial speed, right? And brake to a stop. Right? What happens to the braking distance as a result of making the car really heavy? makes no difference because the mass canceled out. Yeah, the rate the car can slow down has nothing to do with its mass. Therefore, the stopping distance also has nothing to do with its mass. Right? It's really classic physics question right there. Okay? That's just what we got right there. That's the answer. Right? Now, the follow-up question was, how far does the car go? That sounds kinematic. I'm going to make a taxi table. So here's all our kinematic variables we could be juggling. Right? Remember, there's no numbers here, but we just found the acceleration is equal to coefficient of friction times g. So we got that. In fact, it's maybe I could even say negative because it's going to be opposite of the initial velocity. Initial velocity we'll just call initial velocity. Okay. We're solving for how far d. So that's like what we're solving for. Right. What else do you know? There's one more thing you know. It's maximum distance it slides to. You know one more thing. Final velocity, 0 meters per second. Right? Right. Ooh, look, we're juggling a bunch of variables that, okay, we weren't asked for time and we don't immediately have time right away. Does that sound like a job for the third kinematic expression? Vf squared equals v naught squared plus 2ax. Right? You guys have got those three amigos memorized, right? You guys, oh, I got them right here. Bam. Right, you guys have memorized these, right? Right. So looking at that third one right there. Right. So this goes to 0 meters per second. Coming from some general v naught squared. Right. I'm going to go ahead and just include a negative sign right here. Minus, I guess it's that negative sign. I'm just factoring it out. 2. The acceleration is mu times g. And then x, well, I'll call that d, because your book called it d. Right? We're solving for d. How far does that hockey puck slide? Right? I see it? Right. Right. So, well, we're just a couple algebra steps away. 2 mu g d is equivalent to v naught squared. Therefore, the distance it goes is the speed you strike at squared divided by 2 mu g. Okay, there you go. Right. No numbers. You can figure out how far the hockey puck slides. Okay. Has to do with see how. Oh, look, the faster you kick it, the further it goes. That makes sense. The more the coefficient of friction, the less far it goes. Inverse relationship. That makes sense. And the stronger the gravity field of the planet, also it won't go as far. Ooh. I guess I could make that. That can make sense too. Okay. All right, guys, got it. Okay, number 59. We've got the street light held by a couple of cables. Okay, so this kind of reminds me of. Okay. Actually, it's not even this complicated. It's more like this, where it's all symmetrical, right? Okay. Some version of that. Right? So we're back to an equilibrium kind of question. Equilibrium type question. So 59. Okay. I'm gonna start with the Cartesian system, just like we did with the bird feeder. You guys remember the bird feeder? This is gonna be kind of similar to the bird feeder question, right? Okay. A little bit different. They gave us some different things. Okay. They didn't actually tell you the weight of the street light. We don't actually know the weight. Right. Let me draw a little street light going on right here. Something to do with got some lights. Okay. They did tell you the tension in these cables that are at 45-degree angles. Right, so sure if I get this kind of to scale, get this close as I can. 45-degree angles. Right, so something about like that. Right. They said this is 60 Newton tension there. This is a 60 Newtons tension here. We got 45 degrees, 45 degrees, about like that, right? Like that. Right. Or if you like, this could be 45 degrees and this is 45 degrees. Right? Different angles you can play on. Right? So I'm going to split those into components so I can make sense of this. Okay. Remember, the sum of the forces goes to 0 along each axis. So horizontally, this one pulls right as much as this one pulls left. Okay. And then vertically, this one pulling up plus this one pulling up has to balance with that weight pulling down. Right, I said. Okay. So how do they word question A? What is the resultant of the two cables? The resultant of the two cables. Can I take these two cables, maybe start from this origin point and slide this one tip to tail with the other one? Right there. Right. Tip to tail, this guy, and slide this one. Right. Or take this one, slide over. Right. So sometimes you see like a parallelogram, you can do both. Right. Anyway, it's as if there's a single cable pulling straight up, kind of like up to here, right? As if there is. Right? And the way we're going to get that is with our components that I just dashed off. Like this left component, this right component cancel out. Okay. But what about 60 newtons times sine of 45 degrees plus this 60 newtons times sine of 45 degrees, right? Ah, are those both conspiring upward? Right? So I'm going to add those together. So the resultant tension, I call it FT resultant, right, is like this 60 newtons sine 45 degrees plus this 60 newtons times sine 45 degrees. Right. Let's see, what is that? 60 sine 45, that's 42 newtons plus the other 42 newtons. Right, so that's like 84 newtons. Okay, so it's as if there's a single cable that's just holding it up with 84 newtons. Right. Therefore, question B, what is the weight of the light? Guys, what's the weight of the light? Exactly, 84 something newtons. Yeah, right. Because the sum of the forces in each direction, in this case the y direction, has to zero out overall, right? That's true. These two cables collectively are making 84 newtons straight up. Therefore, the light has to be 84 newtons down. Ah. Right? Okay. Guys, go there? All right. Okay, so that's all the ones that I circled and assigned to you guys. Right? So let's go hit number 41 because you guys have a quiz question that's kind of like that. Right? I'm going to do a shortened version of this just to save us a little time here. Right? Beat the bell. Right? Get this 1,000 Newton crate, which side note, I guess the crate's like 100 kilograms. Right? That might be important. Okay? Is push. Looks like 20 degrees downward. So that okay, with the 300 Newton force, right, 20 degrees below the horizontal, right, so that it goes at constant velocity, right? Now, if that's true, then doesn't that mean that constant velocity is not equilibrium? So all the forces have to zero out, right? The only way for that to happen is if there's some friction acting the other way. In fact, the first question is, well, what coefficient of kinetic friction would allow that equilibrium condition, right? Now, I'm going to sort of skip past that. But in the solutions, I got coefficient of kinetic friction is like 0.26 about 0.26, right? So the friction force is like 26% of the normal force, right? Guys, if you're pushing kind of downish, is the normal force going to be greater than the weight? I think so, right? Because if you push kind of downish, that normal force on the floor, now has support like more than the weight. Right? Okay, so that's little steps along the way. Right? Feel free to see how I got that in the solutions, right? But I'm just going to focus on the next part, right, which is more in line with your quiz question. Right? Now we're going to kind of pull up to the right at a 20-degree angle from the horizontal. Right? Now the crate will be accelerating. How much is it going to accelerate? So we got here, floor. Let's go crate, center of mass. Right? Yeah, let's get some Cartesian system going on, I guess. Okay. We're going to pull, was it 300 newtons still, I think? Yeah, 300 newtons. 300 newtons. That's, I'll call it F pull equals 300 newtons, right? That's at 20 degrees to the horizontal. Right? This block has a weight. Now they told you the weight was 1,000 newtons. They went ahead and gave that to you guys, right? So the weight is 1,000 newtons right there. Right? What about the normal force? Do you guys think the normal force is greater than or less than 1,000 newtons? It's got to be less than, right? Because we're partially pulling the block up a little bit, right? So we're sort of alleviating some of the force from the floor. Right? Let's say I break this into components. Right? You can say the sum of the forces in the y direction is zero because the block's not going to be accelerating up or down. Right? So here we can figure out exactly what is this normal force right here, F sub n, right? Which is going to be important to solve. We have to figure that out before we can figure out everything else. Right? So we need this upper component right here. Guys, is this 300 newtons times sine of 20 degrees? Okay. Let's get a number right there. 300 sine 20. Okay. That looks like 103 newtons. I'll just round it. 103 newtons. Close enough. Okay. Well, since the sum of the forces in the y direction must zero out because the block's not accelerating up or down, okay, I can say that whatever the normal force up is, plus 103 newtons minus 1,000 newtons has to zero out. Right? Add that over, subtract that. So the normal force is 897 newtons. There we go. Right, so this is 897 newtons, right? See that? Right. Oh, I forgot to write a couple of details. The mass of the block, of course, is 100 kilograms. And the coefficient of friction, now skip blah, 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 blah. Let's just say it's like, let's call it 0.26. Okay, so let's say you kind of figured that out by this point. Okay. So there is a friction force on this block. Let me go ahead and draw that in. Say it's about a quarter of that. Draw it out like that. Right. Friction force. Guys, is friction force equal to coefficient of kinetic friction times the normal force? Yep. So that's 0.26 times 897 newtons. So take 897 newtons times 0.26. Okay, so the value of the friction, I'm going to round a little bit again. Let's call it 233 newtons, about 233 newtons. Okay. Now we need the net force on this block. So we're going to look horizontally. Oh, I never got this component right here. I need to grab that real fast. Let's go. This is equal to 300 newtons times cosine of 20 degrees. What is 300 cosine 20 degrees? Okay, that's like 282 newtons. I'll call it 282 newtons. Okay, so horizontally, do you see a competition between these two forces right here? Okay, so acceleration is in the x direction is the sum of forces in the x direction divided by the mass. Right? Second law of motion just in the x direction. In that case, it's going to be 282 newtons to the right minus the 233 newtons friction force to the left. There's your net force. And that's acting on a 100 kilogram box. Let's put it all together. All right, so I'm looking at 0.49. That'd be meters per second squared. Right. Now, I did a lot of rounding along the way, so maybe plus or minus a little bit. But that looks pretty reasonable. I think that looks pretty reasonable. Okay. Ooh, just in time. All right, who's got any question? Any question? All right, well, I will post this video to Google Classroom because that's the winner right there. All right, you guys have a great afternoon.